thanks a lot for the introduction and for the invitation. I would have really liked to be there, but well, you know how it is. So yeah, let me immediately tell you about our main theorem, which is a new geometrical application of Khovanov homology, namely for all knots K in the 3-sphere, we have the inequality that lambda of K is less or equal than UQ of K. So you don't know yet what either of these are. So lambda is something from Khovanov homology, and UQ is the proper rational unknotting number. So here's the plan for the talk. First gonna tell you about UQ, then a brief summary of Khovanov homology, then I'll define lambda, and finally I'll prove the main theorem. All right, and yeah, let me encourage you to ask lots of questions. That would be nice. Okay. So let's start with the geometric part with this UQ thing. So when we have two knots K and J always in the 3-sphere, then we say that they are related by a proper rational replacement. Proper rational replacement if one of them arises from the other by cutting out a rational tangle and replacing it with another rational tangle with the same connectivity. So more precisely, if there exists a 3-ball B in the 3-sphere such that outside of the 3-ball, the knots look the same. So outside they are identical. And inside of the 3-ball, so the intersection of both of these knots with the 3-ball are rational tangles. And with the additional condition that they have the same connectivity. So let me tell you what that means. So first of all, a rational tangle is one. So that's a tangle with 4 endpoints, which you can obtain from this simple tangle with 4 endpoints just by adding half twists to the bottom and to the right. So this is obtained from this simple tangle by gluing half twists. So these are half twists to the right and to the bottom. And connectivity simply means which of the 4 tangle endpoints is connected to which. And since we are dealing with 4 endpoints here, there are 3 possibilities. So this is simply, can be this, but let me write it out. So which endpoint connected to which, and this could be like this, this, or this. So let me give you an example of a proper rational replacement. So I'll draw a knot here. Let's take a nice pretzel knot. So this is my knot K. And now proper rational replacement means I take a copy of K. Then I choose a ball. Let's take this one here. Which, as you see, intersects the knot in this rational tangle here, which consists of 3 half twists. And then I replace this by a different rational tangle. Let's say, for example, this one. So these knots K and J are related by a proper rational replacement. And then we say that the proper rational unknotting number UQ is the minimum number of such replacements that I need to do to get from a knot to the unknot. So this is the minimum number of proper rational replacements relating K to U. Okay. So for example, for this knot, since you see, if you look closely, that this is actually the unknot, you see that this knot here has UQ at most equal to 1. And since it's not trivial, it's actually equal to 1. So that's not a very well-known invariant, but it's similar to a much more famous invariant, namely the unknotting number. And you see the unknotting number can also be defined as the minimum number, of certain replacements you need to do to get from a knot to the unknot. But here it's the replacements where you just allow replacing this by this, a half twist by this, by its mirror image. All right. And so now let's have a look at the main theorem again. Create a little bit of space here. Let's put this here. So from the definition of UQ, it's clear that the unknotting number is an upper bound for UQ. And our theorem is a generalization of an earlier theorem by Alishahi and Darwin from 19. Wait, let me check. Is it actually 19? Oh no, it's actually 17. Sorry. The theorem of bless you. The theorem of Alishahi and Darwin is that Ux of K is less or equal than U, where Ux is another invariant coming from Khovanov homology, and we can show that Ux is less or equal than lambda. So you see that our theorem is a generalization of Alishahi and Darwin's in 2 ways. We take something different from Khovanov homology, and which is greater or equal than their bound, and we take something geometric, which is less or equal than the unknotting number. And so the gaps between these three inequalities can be arbitrarily large. So I'm just saying Ali Shai and Dowling here, but there has since been further work by a lot of authors, actually, Caprao, Gonzalez, Lee, Lawrence, Stanovic, Zhang, Gutschral, and Zaka, who have all generalized this. But this was the first of these bounds. Any questions at this point? Okay. Then that's it about UQ. Now let me tell you a bit about Khovanov homology, more precisely about Banathan's version of Khovanov homology for tangles. So my assumption is that most of you are more or less familiar with this, so it will be quite brief. So what Banathan does is that he associates to a 2n-ended tangle diagram D a chain complex, not of modules, but just a complex over some additive graded category. So we write this complex bracket D. So this is a complex over a category C2n, which is additive and graded. And Banathan explicitly constructs this category. It has as objects, it has crossingless tangle diagrams and sums of them and grading shifts of them. So I'm just saying the objects are generated by crossingless 2n-ended diagrams. And the morphisms between two such crossingless diagrams are generated by cobordisms. By certain surfaces embedded into 3 space in a certain way, modulo some relations. Okay, and the way this is done, the Reidemeister tangles get homotopy equivalent chain complexes. So we have the following homotopy equivalences. This is homotopy equivalent to this. This is homotopy equivalent to this, and also for Reidemeister 3, this is homotopy equivalent to the complex of this tangle. And finally, sorry about that. Finally, these complexes glue well. So I mean, if you can cut up a tangle diagrams in several smaller tangle diagrams, then you can read off the complex of the big tangle diagram by taking a certain tensor product of the complexes of the small diagram. So I'll just write that this glues well. And in particular, one of the early advantages of this theory was, for example, that this makes the proof of Reidemeister invariance much simpler, because you just check these homotopy equivalences, and then because of the gluing, you already get that this complex up to homotopy is a tangle invariant. Tangle invariant. Okay. Well, so far this, I assume, is generally well known. And now let me tell you some things which are maybe not as well known. So, I mean, where do you go from here? You have a complex over some weird category, which is not an abelian category. You can't take homology. So how are you going to get a not invariant from this that you can easily work with? Or how do you get a not invariant at all? We've talked about tangles so far. Okay, so of course, a knot is also, it's a zero-ended tangle. So for knot, you get something in C0. And then C0 is still surprisingly complicated category, but what you typically do is you take a quotient. You introduce some dots, so you modify the category a bit, and then you can take some functor and go over to a chain complex of modules. But here's something that you can do alternatively. Instead of using C0, you use C2. So you consider two-ended tangles. And the category C2 is actually nicer than the category C0. So Banathan's category C2 is equivalent to the category of finitely generated free grading shifted ZG modules, where this is a bit, so G is not a group, it's just a free variable. So this is just the one polynomial ring over the integers. And this equivalence is quite explicit. So this tangle, this is an object in C2. This under the equivalence gets sent to just a free module of rank 1. And this cobordism here which is an endomorphism of the tangle above, this gets sent to G. So G is short for genus here.
Okay. I assume that has a certain degree, right?
Yes, there are degrees and everything is graded, but for this talk, I'm just gonna not write the degrees. But you're right, there would have to be degrees. Well, actually, I mean, you're right, there would have to be degrees, but I think what I've written here is there's not anything missing. I mean, you would have to say that G has degree 2. You would have to specify what the grading is on ZG. Okay, is that...
Yes, thank you.
All right. Any more questions at this point? All right. And so now we have decided to work with C2 instead of C0. How do we get a knot invariant? Well, simple. We take a knot and we just cut it open at some point. At any point. And then when we've cut it open, we've got a two-ended tangle. And we can take the Banathan complex of that, which is over C2. So equivalently, it is over ZG. So we cut open at one point, and then we get a complex, which I write brackets K, which is a complex over ZG, which is nice because that means in particular that we can take homology there. And there's a theorem which is, I think, by Naut, a student of Barnaton from 07, which tells you that this way of constructing a Khovanov homology of K is universal. So that means that any other version of Khovanov homology you can construct is determined by this. Determines all other versions of Khovanov homology, and by other versions I mean other Frobenius algebras, arbitrary Frobenius algebras, arbitrary coefficients, and reduced or unreduced homology. Of course, there are other versions like colored homology, which are something else, but all such versions are determined by this ZG homology. And in fact, this is also not something totally new. This is just the reduced chain complex from the Frobenius algebra. ZXG mod x squared minus gx over ZG. Any questions?
Does it matter where you get the knots? Yeah,
that's a good question, of course. That's essential, and it doesn't matter. And there are two different ways you can show this. One is just purely geometrically. If you cut a knot at a different point, you get, well, a different two-tangle, but those two tangles are isotopic. So you can show this just purely geometrically, or you can also diagrammatically take a diagram of a knot, then cut it at two different points. You get two-ended tangle diagrams, and then you can, in this Khovanov theory, show that those two complexes you get are homotopy equivalent. But whatever way you do it, it does not matter where you cut this open. And of course, that's really because we're working with a knot. As soon as we're working with a link, it matters which component the base point, so the cutting point, is on. More questions? All right. So if you're really familiar with Khovanov and Barnaton homology, this might be news to you, this might be interesting to you. If you're not familiar with it, then just forget about all of this and just keep in your head that we have this invariant here, which to a knot associates a complex over ZG. Just keep this in your head as black box. That's all we gonna need for the talk. All right, so where are we in the plan? You know about UQ, you know about Khovanov homology. Now let me tell you the definition of lambda. So we've spoken about a lambda of a knot so far, but actually it's easier to immediately define lambda as a pseudometric on knots. So lambda of k is just lambda of ku, and we are going to define lambda of kj for arbitrary knots k and j. as follows. So you take the two ZG complexes of K and J. So these are finitely generated graded complexes of free grading shifted ZG modules. And now you want to compare them. So of course you could ask whether they are homotypically equivalent or not. So let me write this condition of homotypically equivalence. Homotypically equivalence would be that there exist chain maps F and G between these chain complexes such that F composed with G is homotopic to the identity of bracket J, and GF is homotopic to the identity of bracket of K. Okay, and of course that's not quite what we want, because this would just be an equivalence relation, not a distance. So what we ask instead is we weaken this condition here. We don't ask that F composed with J is necessarily homotopic to the identity, but we just want it to be homotopic to a power of G times the identity. And the same power for GF. And then we take the minimum n such that such map exists. So if this exists for n equals 0, then this is just the condition of homotopy equivalence. So lambda of kj equal to 0 means they have the same Khovanov homology. But greater than that, okay. And there's a last gap I left here. We need to ask that these chain maps are only ungraded. So that means they don't have to respect the quantum grading, and they don't have to respect the homological grading either. They just commute with a differential. Let me give you an example.
But look, at this stage, it's not obvious at all that n is not plugging.
I didn't quite hear you, but I can guess what you said. So at this stage, it's not obvious that such an n exists at all, right? Is that what you asked?
Yeah.
Yes, that's right. So there are two ways to prove that such an n exists. One is a bit funny. It's just, well, let's look at the main theorem. U is certainly finite because it's bounded by U, and every one of us has learned that U is finite. So lambda is certainly finite. That's that's a proof that's not cheating, because in the proof of the theorem we don't require lambda to be finite. So it's really a consequence of the main theorem. But there's also a direct algebraic proof, namely you can show that when you set G equal to 1, so if you tensor with ZG mod G minus 1, then these complexes are homotopy equivalent for any knots. That's a bit non-trivial. That's basically the Rasmussen invariant, but you can show this. And then from that, so you get a homotopy equivalence after tensoring and setting G equal to 1. And then you can lift this to homotopy equivalence before tensoring by throwing in a sufficiently high power of G. So you can also directly algebraically prove it. But so in either case, the proof is not trivial. So that's a good remark.
Just to be clear, it's not. So if I take arbitrary ZG free chain complexes, say finitely generated, this might not exist. Such an n might not exist. Really...
I agree, absolutely. Yes. If you take arbitrary chain complexes, such an n need not exist. Okay. So I mean, but arbitrary chain complexes do not occur for knots.
Yeah.
Right. So let me give you an example. Let us compute together lambda of the travel knot. So let us to compute lambda. Let us write down the chain complexes of K and of U. So the chain complex of the unknot, that's just one copy of ZG in homological degree 0 and quantum degree 0. But as I said, we are completely going to ignore quantum degrees here. The chain complex of the trefoil is homotopy equivalent to one free copy here and sitting in homological degree 0, nothing in homological degree 1, then one copy in degree 2 and one copy in degree 3. And here the differential is G. So this might be unfamiliar to you even if you know Khovanov homology well, but just see that, for example, if I set G equal to 0, then I get the unreduced homology of the trefoil. That's not a coincidence. Okay, so let us now explicitly construct these maps F and G. How could they look like? Well, I'm just gonna let us just try taking the identity here and the identity here. Let us try this first. Those are certainly chain maps. And now if I compose them in this way, I get the identity down here. If I compose them the other way, well, I get the identity on this chain group, but here I get nothing. So that's not good. That's not the power of G times the identity. So I need to do something about this stuff here. But you see, I don't need equality to a power of G times the identity. I don't need equality on the nose. I just need homotopy. So I can throw in a homotopy. So that's what's the easiest homotopy I can find here. It's this homotopy here. Let's just take the map 1 here. That's our homotopy. And now, well, I need to consider H composed with the differential plus the differential composed with H. And that gives me G times the identity here and G times the identity here. That's good. That's a power of G times the identity. But now I have like mixed powers. I have exponent 1 here, exponent 0 here. That's not what I want. So I need to modify my maps F and G. Let's take as map G, let's take big G, and now we are happy. So these are maps F and G and the homotopy, proving that lambda of K is at most 1. And well, since being 0 would mean homotopy equivalence, and these complexes here are clearly not homotopy equivalent, because, for example, they don't have the same homology, we have also the inequality lambda greater or equal than 1. So we have shown this. Questions about this calculation? So you see, if the chain complexes are simple enough, you can compute lambda by hand. For example, the same calculation works for all quasi-alternating knots. For all knots that have thin Khovanov homology, we can show that the ZG complex consists of one of these free copies and then arbitrarily many of these copies. And then we can, well, take such a homotopy for each of those summands, take the maps here. So we can relatively easily show that lambda is 1 for all quasi-alternating knots, for all thin knots. Okay. So far for the definition of lambda, and now for the last point in the talk plan, let's look at how you prove the main theorem. And in order to do that, we need to make lambda a little more general. So right now it's a pseudometric on knots. By the way, I say pseudometric because lambda of two non-isotopic knots can be 0, simply because they are different knots that have the same Khovanov homology. So right now lambda is a pseudometric on knots, but we want to extend it to a pseudometrics on arbitrary tangles. And to do that, we need to have a ZG action on complexes of tangles, like we have here, a ZG action on complexes of knots. And for this, we need to choose a base point. So now we consider a tangle T with one endpoint marked as base point. And I claim if you do that, then you get a ZG action on the complex of this tangle. So you get the complex and this tangle in a new category C to N dot, which is C to N with a ZG action at the base point. So you remember that in this equivalence of categories here, G just corresponds to this curtain with genus 1. So now that you have a base point, a designated base point, you just glue this curtain with tangle with genus 1 to your cobordism at that base point. And that gives you a ZG action on the homomorphisms, on the morphism sets of your category C2N. So more precisely, before it was a abelian group of morphisms, because C2N is additive. So now, by introducing this base point, we have promoted this to a ZG enriched category. So the morphism sets have the structure of a ZG module. And then we can define lambda of two tangles with the same number of endpoints at the same base point, just verbatim exactly the same as we did for knots. I mean, I can really just copy this here and replace K and J by T and T prime. It's really exactly the same definition.
By the way, Lucas, it's not important, but I think in your definition there is a missing minimum before the.
Oh yes, thank you, yes. Yes, of course. Well, I would say this is important. Thanks for pointing it out. All right. And now that we have extended lambda, we can prove the main theorem. It's just 2 steps. So what we need to show is that when we do a proper rational replacement, just remember from the first slide what that is. When we do a proper rational replacement, then lambda between those 2 knots should be at most 1. So as a first step, we show that the lambda distance between 2 rational tangles with same connectivity is at most 1. So I said that lambda is a pseudometric, and it turns out on the set of rational tangles with a fixed connectivity, it's the discrete metric. So that's a quite long calculation to do that. But once we've done that, that's basically it. We just need to glue and use that lambda is well behaved under gluing. So if I glue these rational tangles TT prime together with the rest of the knots K and J, then this is less or equal than lambda of T prime. And that's the proof.
When you glue, what happened to the base point? I mean, you have.
Yes,
R base point for T. So what happens to?
Yes, that's right. I have to be careful that the base point is at the correct. So let me see. So. Yeah, well, basically I have to glue base point to base point. But I can do that.
Okay, but then you need to define what is the base point for the gluing.
Yes. So I mean, yes, I haven't been precise about this. So to get this gluing inequality, you need to be you need to take care of the base point. That's right. So. You want, okay, so I mean, I can, let's see. So what you want is, yeah, maybe, yeah, let me not draw this. But I agree, you need to make sure that the base point of the two tangles you glue is at the correct spot. That's right. More questions? All right, then, well, I can tell you, a little bit more. So, let me give you an example of this first computation, that lambda of TT prime is less or equal than 1 for rational tangles. So I won't show it for general rational tangles, but let me show it for these two. Let us compute lambda of this tangle and this tangle. And now the base point needs to be at the same spot. Let's put it here. So we want to show that this is 1. And once we've shown that, well, we haven't got the full theorem, but we've at least shown the inequality involving the unknotting number. So to show this, I need to deal with chain complexes in C4, chain complexes of tangles with 4 endpoints. We haven't done that so far. So we've seen that C2 is equivalent to this relatively simple category. And now what about C4? or more precisely C4 dot. And fortunately, this is also a relatively simple category. So this is a theorem by Kotelski, Watson, Zibrovius. So they state it a little bit differently. And it says, it gives a simple language for C4 dot. Namely, this category C4 dot is equivalent to the ZG enriched category generated by, so we need two objects, this one and this one. So these are two objects, and then I said generated by. So what I mean is it's an additive category. Of course, you can also take sums of these objects. It's a graded category. You can take shifted sums of these objects. But that's it. They are shifted sum. Every object is a shifted sum of these two. And now for the morphisms, you just need the identity morphisms and morphisms here, which I will call S. As you can imagine, S is for saddle, because that's actually the cobordism it corresponds to in Van Nathan's model. So for cobordisms, you have these two saddles, and then you have all compositions of saddles, and you can sum and you can multiply by G. So that's what I mean by generated as a ZG enriched category. And you only have the one relation modulo that S to the 3 is equal to GS. I mean, actually, it's two relations because, you know, by abuse of notation, S denotes two different cobordisms. So it's actually two relations, but that's it. And this is geometrically quite clear if you think about it. If you stack three saddles, it's the same as one saddle with an additional genus. Okay, so that gives us a good language to write down complexes of tangles with 4 endpoints. And oops. Yeah, so let's actually do this. Let's compute this here. And that's the last thing I'm going to do in the talk. So let's write down the two complexes, and they are actually by definition equal to this complex here and this complex here. So that's the usual scan relation in Khovanov homology. And now, how do we find maps F and G and a homotopy so that we have this condition here? We want FG to be homotopic to G times the identity. Well, let's have a look. Let's have a look what chain maps we can write down at all. So, for example, we could try to go from here to here with a saddle, but that's not a chain map because it doesn't compose to 0 with the differential. But remember that we only want ungraded chain maps. So that wasn't relevant if you think back to the trefoil. In the case of the trefoil, our chain maps were actually graded. So here in this example, they are not going to be. So my map F is going to be 1 here. So that's a chain map because it composes to 0 with the differential. And here I want something that composes to 0 with S. So I just take G minus S squared. So G minus S squared times S is GS minus S to the 3, which is 0 by assumption. So this is the chain map F. And then the chain map G is going to be just the symmetric version of F. So it's going to be G minus S squared here and 1 here. So that's G. And now what you get when you compose F and G, you just get, well, if you first do G and then F, you get G minus S squared here and the same here. So this is just equal to G minus S squared times the identity. So that's not quite what we want yet. The S squared is annoying. We want G times the identity. But here comes the helping homotopy. Just as a homotopy, we take S here. And this homotopy shows us that S squared times the identity is null homotopic. So this is null homotopic. So F composed with G is homotopic to G times the identity of the complex of this tangle, and GF the same. So that's the example. And so this is basically, this is what Ali Shahi and Downing do. They come up with this diagram. And now in our paper, to go over to rational unknotting, we need to find such maps FG and homotopy for all rational tangles with same connectivity. Okay, that's as far as we're going to go. Thank you very much for your attention.
Questions for Lucas? So do you have any ideas about sort of a rational link splitting invariant?
Could you elaborate a little bit?
So there's some work of Batson and Seed from many years ago about some deformations of Khovanov homology, which gives bounds on how many about splitting links into something unlinked. Now maybe there's a rational tangle version of that.
Yeah, that's a good question. I haven't really thought about this. So you mean like they have a lower bound on the number of crossings you need to change to get to something split? Yeah. And we could do that with proper rational replacements. Yeah, I mean, that sounds reasonable. I mean, we would have to deal with links then, but that's not, yeah, that's something that should be doable. I mean, in the article, we stuck with knots, but sounds reasonable that you can do something for links.
And maybe it's not exactly a question for you, but is there an analogous theorem from Koletsky, Watson, Zimbovius for, say, C6 or C2n?
No, I don't think there is yet, but I think this is something at least Claudius is interested in. So let me tell you a little bit more about the theorem. So the reason they're interested in this C4 explicitly is because they don't stop here. This is just the beginning. They have a whole way to encode complexes over this category of C4 in a geometric way as multi-curves on a punctured sphere, which allows you to deal very effectively with these complexes. So that's the reason they're interested in C4 to develop this calculus. And I don't think that, as far as I understand, that's not going to generalize very easily to C6 or C8 or so on. So that's why they didn't go further here. But if you're just interested in this, I think it's doable to write down an analogous theorem for C6. I mean, for C6, okay, you're going to have 5 objects, not 2, but you're going to have these 5 objects here. This one, this one, this one, this one, and this one. And then, of course, you're going to have more morphisms and more relations, but it's going to be a finite representation, just like the one here. You just need to figure out what it is. But I think you can, you could say that for any n, C2 n dot has a finite representation in this way. That's certainly true. Yes.
Is one more question. It raises problem for so-called tangle equations when you have some knot from which you remove some pieces, and the question is, can you fill in those pieces with rational tangles to get some result? So I think this kind of problem is that appears quite often in the, for example, DNA analysis. You have some diagram and you want to check whether this diagram, this picture of DNA or some protein can be particular knot. And it's quite hard to actually solve those equations, to find the fillings that gives you particular knot. Is it possible that your result can give some obstructions to existence of such equations? Because it looks like your result can be applied to problems where you want to replace some piece of a knot, a tangle, and check whether you can get a desired result.
Yeah, so yeah, I'm sorry, I'm not sure I really sufficiently understood the question to give a good answer.
So the problem is that we have some diagram of a knot or a link from which we remove some disks.
Mm-hmm.
Each disk have 4 endpoints of the original knot, and the question is, can you fill in those disks with rational tangles so that the resulting knot is a particular knot you want to get?
Okay.
So if you have such collection of rational tangles that when you fill in those holes, you get a particular knot, you say there is an equation to this tangle equation. It is a solution to tangle equation. And the problem is, does in general do such solutions exist? If it exists, how many of them, and so on. So my question is, can your result give some obstructions to existence of such equations or such solutions?
Yeah. Okay. I think so. Yes. I mean, so if I understood correctly, you have a knot decomposed into 2 tangles, which are not necessarily rational. Now you want to replace one of the tangles with a rational tangle, so that the resulting knot has a certain property. And I mean, with our result, I mean, surely we get restrictions on lambda of the resulting knot, even if the tangle that you replace is not rational. I mean, you would have to explicitly look at that tangle and look at the bracket of that for in the tangle. But well, if it's a concrete example, you could explicitly do this, and I think we would get some restrictions. I mean, then the restrictions are on lambda of the resulting knot. So I'm not sure if this is, you know, if this is what you're looking for. But I mean, it would give you some restrictions on the Khovanov homology of knots you could obtain like this. That's certainly true. Yeah.
Do you have any impression how difficult, how computable that is? Is it like difficult to compute, or Could it be algorithmic?
I think it's algorithmic. So we haven't written this down, and we haven't implemented a complete algorithm. So you can't just feed it into the computer and it's gonna spit out Lambda. But like in practice, if the example is not too big, computing Lambda is fairly fairly straightforward. So because the reason is that I mean, first of all, we have computer programs that compute this ZG complex and simplify it, and then we have another program written by Damian Iltgen that decomposes the ZG complex into summons. Yeah, that's a non-trivial thing because it's not a PID. And then the nice thing about Lambda is you can compute it on each summoned, and Lambda of the sum is just going to be maximum of Lambda of the summons. And the summons tend to be relatively small for nodes. And then you can do it by hand on the summons. So I mean that was a comment how easy it is to compute Lambda for nodes. The answer is it's not completely automatic, but it is algorithmic, and in practice it's fairly doable. And I mean, in your case, I think you would have to look at tangles. So there's more manual labor involved, but it's certainly something you can do given sufficient motivation. But I mean, you have the whole day free in the conference, right? You have a break from lunch till 5, so you can do it in that time.
Let's thank Lucas for a nice talk. I'll begin.
Yes, 5 minutes.
5 minutes?
Yeah.
Next talk we get 10 out.
Which program are you using to write in? Is it?
Which program for calculating the ZG complex?
Yep.
So I'm using a program I wrote myself. It's called Coca. There's also a program by Claudius Zibovius which you can use, which is but like the programs, yeah. So the programs you would like usually use to compute Khovanov homology, like Banathan's programs, Scott Morrison's, and so on, they don't quite give you the complex over the integers with a variable. They, for example, they give it over a field with a variable, but it's not enough. You really wanted the universal thing over the integers, and they don't quite do that.
Just like
Is it possible that the same statement holds for alternating four-ended tangles?
That's a good question. So I don't know off the top of my head, but I like intuitively I would say no, but I don't have a counterexample which I can just give you like this.